Hello everyone, welcome back. So we are in lecture 3 of week 1, and in the previous lecture we have discussed how to model a reinforced concrete section using working stress method, right? And hope you have already gone through all the derivations. If I quickly sum it up, we started with the linear stress strain behavior, that is the fundamental assumption behind working stress method. So strain profile is always linear between the extreme compression fiber and the rebars at the bottom. Then our first task is to find out the location of the neutral axis. For that, we define different types of sections, either critical sections or under reinforced or over reinforced section. For a generic case, we can find out the location of the neutral axis by solving a quadratic equation that we have developed. And we have also derived the critical depth of the neutral axis based on the property of steel that we use. It does not depend upon the quality of concrete as per Indian codal provisions. Now, once we find out the location of the neutral axis, we first check whether it is balanced under reinforced or over reinforced section. And depending upon the situation, we can find out the sectional resistance, right? And that's the capacity. And when the capacity is more than the demand, we have the safe design. Otherwise, we have to repeat the procedure. Now, today, let us take some example. So, our first example is for a rectangular beam of size BD, and again, the strain profile is linear. So, we have a modular ratio based design. So the problem is evaluate critical sectional parameters for the given profile with M40 concrete and Fe 250 steel. Now, for this derivation, we will use IS 456 2000 guidelines. Okay. Now, first thing first, we have M40 concrete, and for that, as per the above guideline, sigma CBC is equal to 13 Newton per millimeter square. And also code specifies the modular ratio, which is 7.18. So based on these two values, we can find out what is M sigma CBC. So which is equal to 7.18 times 13. So that is equal to 93.33. Recall, this is the value we used when we derived the expression for K in the last class, right? And what was the expression for K or Kc here? Because this is a critical section, we derived the expression. It is M sigma CBC divided by M sigma CBC plus sigma ST. So M sigma CBC is 93.33 divided by 93.33 plus sigma ST, we use Fe 250 steel, and for this sigma ST is 140 Newton per millimeter square. So what we get is Kc is equal to 0.4. So that's the value of Kc. Now what is the JC, sectional property that defines the lever arm? If you recall, we have a compressive force here. Sorry, let us draw it here. So we have a compressive force here and we have a tensile force there, and the lever arm is actually the distance between these two, equal and opposite force, right? So J is 1 minus K by 3. We derived that very easy because this force will go through the CG, which is Kd is the depth of the neutral axis, Kd by 3 is the location of this force. So 1 minus K by 3 is 1 minus K is 0.4, so 0.4 by 3, and if we find out, it is 0.867. Now we can find out what is RC. RC is equal to half Kc JC and then sigma CBC. We know all of them. If we put this, and you'll get 2.254. And then finally what we have is PT. PT is what? We derived the expression, and that is 50 m sigma CBC square divided by sigma ST times m sigma CBC plus sigma ST. And if you put all the values, we know what is the value of m. It is 7.18, sigma CBC is 13, and sigma ST is 140, right? So if you put those values, what ultimately is 1.857%. So we get the critical percentage steel, actually percentage steel for critical section. Okay, so that solves all the critical parameters for this section having M40 concrete and Fe 250 steel. Now once you find out this sectional parameters, that is Kc, Jc, Rc and Pt, you can also find out the moment of resistance for this section. I leave it as an exercise, so you can either consider sigma CBC, that is the compressive force, and find out what is the lever arm, that is JD, and you can find out moment of resistance of the section. You can also consider the tensile force in the steel and multiply that with the lever arm, you'll get the sectional capacity. Okay, so that you can do it at your end, but the sectional parameters we have already derived as per the requirement of this problem. Okay, so let us go to the next problem. So example 2. Determine the moment of resistance of a singly reinforced beam. So of a beam 200 mm wide and 375 millimeter deep. This is effective depth. Okay, so it is given effective depth. That means from the top fiber to the center line of the rebar. So this is B and D, they are given. Now it is made of M30 concrete and Fe 250 steel, and there are 4 rebars of diameter 20 millimeter. Okay, so our task is to find out the moment of resistance. So let us do that. So First thing, we can calculate what is AST. AST is, we have 4 rebars, each having a diameter of 20 millimeter. So pi by 4 into 20 square, which is equal to 1256 millimeter square. Then we have M30 concrete. For that, code specifies sigma CBC is equal to 10 Newton per millimeter square. And then modular ratio M is equal to 9.33. For Fe 250 steel, sigma ST is equal to 140 Newton per millimeter square. So from this information, we can find out what is PT, percentage steel, and that is 1256 divided by, we have width 200 times depth 375 times 100. And if you solve this, you will get 1.675%. Now, we can also find out stress ratio, or if you recall, stress ratio is sigma ST divided by sigma CBC. So here we have 140 is sigma ST and sigma CBC is 10. So R is 14. It is RC because let us try with balance section first, and then we will see whether it is a under reinforced or over reinforced section. That we'll do in a minute. So KC is equal to M sigma CBC divided by M sigma CBC plus sigma ST. And if you put the values, what you will get is KC is equal to 0.4. Now, we can also find out the location of the neutral axis NC, which is equal to KC times D. So, we have 0.4 times 375, so it is 150 millimeter. Now, we have to find out the exact location of the neutral axis and check whether it falls with this balance section or not, and accordingly we have to decide. So for that, let us first find out the location of the neutral axis. K, if you recall, we solved the quadratic equation and the expression that we derived is mpt square plus twice mpt minus mpt. Now we know all the parameters. So m is 9.33 times we have 1.675 square of this plus 2 times 9.33 times 1.675 bracket close minus we have m times pt, so 9.33 times 1.675. And if we solve this expression, what we get is 0.97. So if we go back to the previous one, we have already derived Kc here. Kc is 0.4. So K is certainly greater than Kc. If K is greater than Kc, that means if this is the location of the neutral axis, that is critical, then say let us write in black, and then we can draw another line using red. So original neutral axis is somewhere below because K is more than Kc. Now, if this is the situation, you know if neutral axis is here compared to the critical value of the neutral axis, then what we have, so this is critical. Then our conclusion is this section is a over reinforced section. Now, if it is over reinforced section, then what happens? Sigma C is equal to sigma CBC. And moment of resistance MR is actually based on concrete. So it is R B D square. We have to once more find out R based on this K value. Earlier we derived the previous problem R, that is half Kc Jc sigma CBC, that is for balanced section, but here we have over reinforced section with this value of K. So it is half then K J sigma CBC. So what we have, half K is 0.97, J is actually 1 minus K by 3, so 0.97 divided by 3 times sigma CBC. In our case, we have M30 concrete, so sigma CBC is 10, so multiplied by 10. So we have R is equal to 3.298. So now we can find out moment of resistance of the section, and that is 3.298 times the width of the section. B is equal to 200 millimeter and small d, that is the effective depth, is 375 millimeter. So 200 times 375 square. And if you find out, it is 92.76 into 10 to the power 6 Newton millimeter. Now if we remove this 10 to the power 6, what we have is in kilonewton meter. So that's the moment of resistance of the section which we are supposed to find out, right? Okay, so now let us go to the next problem. For this problem, example 3, the statement is, for the same problem in example 2, find the maximum value of the UDL that a beam of 6 meter can carry. In addition to its own weight. So we have a beam, simply supported beam, and it is supposed to carry a UDL, and we have to find out the intensity of the UDL if this distance is 6 meter. Now obviously the maximum bending moment for this deflected profile will be at the center, so BM max is equal to omega L square divided by 8. But the fact is it should also carry its own weight. So let us first find out the combined value of the UDL that it can carry if the sectional capacity is what we have derived already. So this is 92.76 kilonewton meter, right? So MRC is equal to 92.76 kilonewton meter. Then if we equate omega L is 6, omega 6 square by 8 is equal to 92.76. We get omega from this expression, and this is nothing but 20.61 kilonewton per meter. Now it has a combined action of UDL coming from the external force and the weight of the structure. So we know the cross section, which is 200 millimeter, and density of the concrete, reinforced concrete, is 25 kilonewton per meter cube. It is given in IS 456 2000. So we can find out omega dead load, and that is nothing but cross section 0.2 times, we have the depth is 375, and we have to design the steel. If we see, we have 25 dia, so this diameter of the steel is 25, and if we have, say, a clear cover of 40 millimeter, so clear cover is 40 millimeter. So 40 plus half the diameter, that is 10, we have to add this D effective to get the complete depth. So for us, complete depth is 0.375, or let me write 375 plus 10, that is half the diameter of the bar, plus say 40 millimeter. There is a specific clause for clear cover, but for the timing, let us assume it to be 40 millimeter clear cover divided by 1000 is the total depth of the beam. Now that times 25 is basically the UDL coming from dead load. And if you do this exercise, you'll get the value, which is 375 plus 10 plus 40, that is 425 divided by 1000. So 0.425 times 0.2 times 25. So this is 2.125 kilo Newton per meter. So now we can find out omega UDL is equal to the total. We have 20.61, that is the total value of UDL we can apply depending upon the sectional capacity that we have already derived, minus 2.125 is basically the effective UDL. So it is 18.485 kilonewton per meter. So that is the answer. So you can see how we can derive the external load that we can safely apply using working stress method, right? Okay, so now let us take a different example, and in this example what we'll do, we'll design the singly reinforced section. So our fourth problem is design singly reinforced section of a beam with effective span length L effective is equal to 6 meter and made of M30 concrete and Fe 250 steel. The beam carries an UDL of 9.5 kilonewton per meter, including its own weight. The size is 200 millimeter by 400 millimeter. Okay, so this is B, this is D effective, epsilon C, epsilon S, then we have sigma C, sigma ST divided by M. So let us solve this problem. So for the given parameter, what we have, sigma ST is equal to 140 Newton per millimeter square. Sigma CBC for M30 concrete, it is 10 Newton per millimeter square and the modular ratio is 9.33. Now M applied is omega L square by 8, and if we use a omega of 9.5 kilonewton per meter over a 6 meter span, what we get is 42.75 kilonewton meter. So what is MRC? It is, if you recall, R BD square. R we can find out, R is equal to, or RC for that matter, half KC JC times sigma CBC. This we have already find out, and KC for this section in the previous example we have done, that is 0.4, and JC is 0.867. We have already found it out, so it is 1.734. Now let us try with the effective depth of 600 millimeters. So try with D effective is equal to 600 millimeter. Then MRC we can find out, it will be 1.734 times we have B, which is 200, times 600 square, which is equal to 124.85 kilonewton meter. Now you can see this sectional capacity is far exceeding the value that we have applied, and therefore obviously this section we are not going to use. 600 is too big for this section, because although this section is safe, but still you see the third objective of design is also economy. We cannot provide such a huge section for small applied force. So we can now redesign the section based on the depth which is proposed to be 400 millimeter. So let us try that, and we'll see how we can find out the complete sectional property and design this section. Sorry. Okay, so for 200 millimeter by 400 millimeter, let us solve the problem. So for that, we have to find out k, and k is 1 by 1 plus r by m. Okay. Right. And then we can find out the location of the neutral axis. So what we have M applied, we'll do that in a minute. So M applied at the section level, so MR is equal to half B times N times sigma C times D minus N by 3. Right. And this we have to equate with the externally applied. So this is equal to the externally applied moment, and which is we have already derived 42.75 kilonewton. That will tell us the only unknown, which is n, and we will find out the location of the neutral axis. So 42.75 into 10 to the power 6 is equal to half. We have B, which is 200 times n, and then for sigma C, we can write down n times sigma st, which is 140, divided by m times, so 9.33. Within bracket, we have d minus n, so that is 375 minus n. How do you get 375? We have this total depth 400, so we leave this space for the cover, which is clear cover plus half the distance. So this is not exact, but for the timing, let us leave 25 millimeter. We can leave more also. Let us try with this, and then if required, we need to adjust. So minus 375 minus n by 3 here. Now, if we solve this, we'll get the quadratic equation of k, but this time I write in terms of n. Recall n is equal to k times d. So we are familiar with the quadratic equation of k, just I thought to recast the same equation in terms of n, and let us see what happens. So we have n square times 1125 minus n divided by 375 minus n is equal to 85649.5. So if you simplify this expression, you will get this equation. Now, you can ask me at this point that we earlier derived an expression of k using m and pt, a quadratic equation, if you recall. But in this design problem, as of now, we don't know what is the amount of steel that we have provided, because this is the design problem. We are supposed to provide that design. Okay. So that's the reason we cannot find out PT, and for that reason, we have to cast this expression using the moment balance equation and in terms of n. Now, this is a cubic equation, and we have to solve it using heat and trial. So we can try different values of n, and then we can find out the solution. Otherwise, we have to solve this cubic equation. So if you go by trial and error method, approximately this value will be very close to 142.37. So this is the trial and error solution. As I said, if you can solve this cubic equation directly using your calculator, you can straight away get the exact value. Otherwise, we have to go for an approximate solution. So start with n square, get some idea just by taking square root. Obviously, this correction factor will come, and then you have to adjust that value and find out the solution. So this is not an exact solution, but an approximate solution for n. And corresponding k, now you can find out n by d, and which is 0.379. Now, if you look at this value of k and the kc is 0.4, so this is less than kc. Kc is equal to, we have already derived, that is 0.4. Now, if this is the situation, K is less than Kc, we call it under reinforced section, right? Now, for this section, then we have to first find out the stress profile. For under reinforced section, steel will reach its maximum value, and so we have to find out this sigma c, because it is not sigma cbc anymore. So sigma c is equal to this n, which is 142.37 times sigma st, our case it is 140, divided by 9.33 within bracket 375 minus 142.37. This we get from the stress profile, and if you find out this value, it is 9.18 Newton per millimeter square. So what we do, we start with this stress profile, and from this we actually find out what is this sigma c. So now we have sigma c, and we can calculate what is AST. AST is what? It is half B times KD times sigma C divided by sigma ST. So now we know everything. So we have half B is 200 times KD is equal to N. We know N, that is 142.37 times sigma C is 9.18 divided by 140, which is equal to 933.54 millimeters square. So try with for number 18 millimeter bar. So the area provided, or AST provided, is equal to 4 times pi by 4 times 18 square. So this is equal to 1017 millimeter square, which is more than AST required, and therefore the design is okay. So you can see how we started with basic geometry, and then we derive the amount of steel that we need to provide for this particular design. So that clearly tells you, if we start with a complete geometry, how to find out the moment of resistance at a particular section, and if we know the applied bending moment, and then if we start with the geometry, then we can find out the amount of steel that we need to provide, which is actually the main objective of our RC design. And for this problem, I have already explained that you cannot arbitrarily provide any depth. We have started with a very large depth of 600 millimeter, and you have seen it provides a section which is safe, but it is uneconomic. So design always finds out the economic use of the material, and that's why we need to readjust all the parameters so that we get the effective design. And in this case, we get 4 18.5 bars will be sufficient enough. Now recall, we started with 400 as the total depth, and then minus diameter of the bar is say 9, and then say if we provide 15 millimeter clear cover, so we have 376 millimeter as D effective. In all our calculations, we have used 375 as the D effective, so it should be okay. Right. Otherwise, I mean, if the clear cover is more, we need to provide. For some structures, we need to provide more clear cover, and there is a specific guideline in the codal provisions. For example, if you design a structure for marine environment, you need to provide more clear cover to protect your steel. So in that case, you have to readjust. We cannot provide a depth of 400 millimeter because that gives us the amount of steel. So we have to readjust the clear cover. That will reduce the effective depth, and we have to redesign the amount of steel required for that particular section. So this is the way we adjust the design, which is a iterative procedure. We try with certain proposals, and then we check whether that proposal is sufficient enough. If it is sufficient enough, we have to check whether it is economic or not. Otherwise, we have to readjust all the parameters and then redesign to achieve the most economic design for our case. So with that, let us close our discussion today. We'll further extend it and we'll see how we can use this working stress method for the design of the section. And then gradually we'll see what are the merits and demerits and why we need basically limit state method, which is the main objective of this course. So let us continue in our discussion in the next class, and we'll see further what are the advantage and disadvantage of this working stress method. Thank you very much.